Hey there, welcome back. If you are new here, my name is Harcourt, and this is Harcourt University. Over here, we break down complex mechanical engineering problems to make them well understood. Now, my realization is most of you don't subscribe to the channel after viewing. So this time, I want to throw up a challenge. At the end of this video, if you enjoyed, you let me know in the comment section. You like and subscribe to this channel to support what we do here. Today's session, we are going to solve some questions under mechanical or under vibrations, which are specifically free and damped systems. A connecting rod of mass 40 kg is suspended vertically as a compound pendulum. The distance between the bearing centers is 800 mm. Okay. The time for 60 oscillations is found to be 92.5 seconds when the axis of oscillation coincides with the small end center, and 88.4 seconds when it coincides with the big end center. Find the distance of the center of gravity from the small end center and the moment of inertia of the rod about an axis through the center of gravity. Assume damping effect of the bearing is negligible. Also, if the damping is present in the bearing, or if the damping present in the bearing is significant, determine its damping effects or damping factor, when the time for 60 oscillations is found to be 92.5 seconds. So in this problem, the connecting rod is of mass 40 kg. So the mass is 40 kg. The distance between the bearing centers is 800 mm. So for any connecting rod, there is a part that has a bigger bearing and there is a part that has a smaller bearing. And the question says the distance between them is 800 mm, which is equal to 0.8 meters. So each part of the connecting rod is hung on a pivot point, let's say a rod, to make it swing, as you can see here. So when the smaller one was hung on that pivot point, the time for 60 oscillations, so let's say T1 is 92.5 seconds. And when the bigger one was used, T2 for 60 oscillations is 88.4 seconds. Now we are looking for the distance between the center of gravity and then the center of the smaller bearing. So let's label that as H. So if the center of gravity is somewhere here, then you're going to have mgh here. So from here to here, let's have this as H. Okay, so the period, which is T. In fact, before we go to that, the equation of motion for a pendulum, a compound pendulum, is given as I theta dot I theta dot plus mgh theta equals 0. So from here, our natural frequency will be equal to square root of mgh over I. So this will be our frequency. Now, we know that for every one complete cycle, we complete an angle of 2 pi. And the time is what is known as what? Period. So 2 pi over the period should also be equal to omega n. So in that sense, we can say that the period is equal to omega n over 2 pi. So from here, we can say the period is equal to 2 pi over omega n. Now, let's deal with them one by one. So I'm going to take the oscillation when the smaller side was used. So for smaller bearing center, let's label this point as O. So you have the equation of motion will be I naught 1 theta dots plus mgh theta equals 0. So from here we can say that the period 1 is equal to 2 pi square root of, so here the omega n is a division, right? So if you bring it, it will be a reciprocal. So instead of mgh over I, if it comes to the period, it will become I over mgh. But here is what's O1, right? I at O1 for the smaller one. So the moment of inertia when the smaller one is used about the point O will be equal to mk squared plus mh squared. So if you make that substitution, we can say T1 is equal to 2 pi square root of mk squared plus mh squared all on mgh. So m will cancel m and m. So from here we can see T1 is equal to 2 pi square root of k squared plus h squared all over gh. So the period T1 is equal to 92.5 over 60 because the time for 60 oscillations is 92.5 and the period is time for one oscillation. So this one gives us 1.542. So from here we can say 1.542 squared all over 4 pi squared is equal to k squared plus h squared all on gh. So I brought this, I squared both sides to take the square root out. This one will become 4 pi squared, and the period is what I found to be 1.548 squared here, this one squared, and I have this here. So I want to have a single equation that I can deal with. So over here, I will have 1.542 squared out of 4 pi squared to be 0.06, and I can maybe multiply 9.81. So I have 0.590 h to be equal to k squared plus h squared. So equation 1. Now the k is radius of gyration. So we'll go and deal with the bigger bearing center. So for bigger bearing center, our I will be I naught 2 theta dot plus mg. Now this time, because, so as I stated earlier, from here to here is 0.8, and we stated that from here to when we use the smaller bearing center, the distance from the center to the center of gravity is h. That means the distance from the center of gravity to the center of the bigger one will be what? 0.8 minus h. So here our h, let me draw that. Let me show you that. So if you draw the bigger bearing pivoted at the point, the distance, this will be the center of gravity. The distance from here to here will be 0.8 minus h. All right. So whatever you were doing with the h in the smaller one, this time you use what? 0.8 minus h. So over here we had mgh. So this time it's going to be what? 0.8 minus h theta equals 0. So of course T2 will be equal to 2 pi square root of I naught 2 all over mg times 0.8 minus h. Now T2 will be equal to 88.4 out of 60, and that will give us 1.473. 1.473 seconds, right? What else? We know I naught 2 is equal to mk squared plus m into bracket 0.8 minus h squared. So from here we can say T2 is equal to 2 pi square root of mk squared plus m into brackets 0.8 minus h squared all on mg 0.8 minus h. Don't go and cancel this and this, oh, I beg you. But what we can, if I can factorize the m out, so m will cancel m and m here. So t we have 1.473. Let's just square that all over 4 pi squared to be equal to k squared plus 0.8 minus h all squared. Oh, maybe let's bring all divided by g times 0.8 minus h. So 1.473 squared divided by 4 4 pi squared 1 1.473 squared divided by 4 pi squared equals to this, right? So we have 0.055 here. Maybe times 9.81 multiplying 0.8 minus h should be equal to k squared plus 0.8 minus h all squared. So 0.055 times 9.81. So we have 0.53955 multiplying 0.8 minus h to be equal to k squared plus, if we expand this, 0.8 squared, that is 0.64. So 0.64 minus 1.6h plus h squared. Okay, so we have equation 1 and equation 2. So easy like that. The only thing we have to do is solve for the unknowns, which is h and k. So from equation 1, we can say that h should be equal to 0.590h minus k squared and substitute in equation 2. So that would be 0.539, let me say 6 here, multiplying 0.8 minus h to be equal to k squared plus 0.64 minus 1.6h, this time plus h is what, 0.590h or 0.59h minus k squared. All right, so from here you can see that k squared will cancel k squared here. So when we expand this bracket, we have 0.593, 0.5396 times 0.8. So we have 0.431 or 32 minus 0.5396h to be equal to 0.64 minus, so we have minus 1.6 plus 0.59 each. So here you can, anyway, let's just write, so 1.6h plus 0.59h. So we put all the terms with the h to one side, all the terms without h to the other side. So I have 0.432 minus 0.64 should be equal to minus 1.6h plus 0.59h plus 0.5396h. So over here we have 0.432 minus 0.64. That will be minus 0.208 to be equal to, here we have minus 1.6 plus 0.59 plus 0.5396. So we have minus 0.4704h here. So h is equal to 0.208 all over 0.470, and that is 0.208 all over 0.470 at 0.442 meters. So from here, oh, here it was supposed to be h squared, all right? So we know h, so we can easily get k, right? So we can say that k squared will be equal to k squared will be equal to 0.590h, sorry. So yeah, 0.590h minus h squared. So k will be equal to square root of 0.590h minus h squared. It will be square root 0.59 multiplying 0.442 minus 0.442 squared. So we have 0.256 meters. So the radius of gyration, in the question we have to find the distance of the center of gravity from the small n center and the moment of inertia about an axis through the center of gravity. So the E part is this, the distance, the first distance is this, and we want the moment of inertia at the center. We know I not supposed to be Ig plus md squared, and Ig is equal to mk squared. So our Ig will be equal to 40 multiplying 0.256 squared, and that will be 2.621 kilogram meter squared. Now, the next question says, if the damping is present in the bearing or the damping is significant, determine the damping factor when the time for 60 oscillation is found to be 92.5 seconds. So when the damping is present, the equation of motion becomes I theta dot dot plus C theta dot plus mg h theta, which is equal to 0. The C is supposed to be equal to 2, no, sigma multiplying Cc, and Cc is equal to 2I squared omega n squared. So we can say C is equal to delta zeta, multiplying 2I squared omega n squared. So we just have to get to this and everything will be sorted. The omega n, of course, is going to be square root of I over, sorry. So the natural frequency, omega n, is going to be square root of mgh over I naught, right? Now, I naught 1. I naught 1 will be equal to Ig plus mh squared, which Ig is 2.64, so 2.621 rather, plus 40 times 0.442 squared. And this should be equal to 2.621 plus 40 times 0.442 squared. So we have 10.44 kilogram meter squared. So we know the I, we can easily get the omega n. So omega n is going to be square root of 40 times 9.81 times 0.442 all on 10.4 4.075 rad per second, technically 6. All right, so we know the omega n, we know this. Now for the when the damping is present, we don't use omega n, which is the natural frequency, alone for the period. Now the period now becomes 2 pi over omega d, where omega d is known as damped natural frequency. Now omega d is equal to omega n square root of 1 minus zeta squared, right? We know omega n already. The period is the time for the instance where the smaller bearing is used, which we said it was what? 92.5 out of what? 60. So this is equal to 2 pi out of what? Omega n root 1 minus zeta squared. The zeta is done like this, something like this. So from here, our task is to find the zeta. The question asks us to find the damping coefficient or damping factor. So we need to find the damping ratio. Then we can use the damping ratio here to find the damping factor. Everything here is known except for that guy. So yeah, from here we can say 92.5 out of 6. That will be 92.5 out of 60. That is 1.54167. 1.54167 equals 2 pi out of 4.076. 0.76 multiplying square root of 1 minus zeta squared. So we will have square root of 1 minus zeta squared to be equal to 2 pi all on 1.54167 multiplying 4.067. So take square of both sides. We have 1 minus zeta squared to be equal to 2 pi out of 1.54167 multiplying 4.076. So we have 0.999789 here. So we have 1 minus 0.999789 to be equal to zeta squared. The square root of both sides. We have zeta to be equal to square root of 1 minus 0.999789. That will be 0.0145. All right, so knowing zeta to be 0.145, and also C is to be equal to this. Said C, the damping factor is equal to damping ratio times 2I squared omega n squared. So C will be equal to 0. So 10.44 squared plus 4.076 squared. So we have 3.402 kilogram per second. So if you enjoyed the session, kindly subscribe to this channel. If there is any problem that you are not clear with, kindly let me know in the comment section and I'll clarify. Also, I want to emphasize that getting to find a damping factor, you need to be careful with the approximations you make. Little approximation can change the value, so don't approximate too much or approximate correctly.